just so we can post online afterwards. So I would just like to introduce Mike Clatworthy, who is the National Sales Director for Multistack. He is joining us today from Sparta, Wisconsin. If I could just pass it over to you, Mike, that'd be great.
Thank you, Alex, and thanks everyone for joining us today. I want to spend the next 20 to 25 minutes talking about something that we call dedicated heat recovery and related technology that we've developed that grew out of dedicated heat recovery. So what it's really about is saving energy and reducing carbon footprint. Now, I think I'd like to start out first by taking a moment to introduce Multistack. Who is Multistack? Multistack is based in Sparta, Wisconsin. We've been in business for 20 years. We are manufacturers of specialty water chillers, modular water chillers, and heat recovery equipment. We've got the honor of being the basis of design for the secure communications facilities at U.S. embassies around the world, and we're very proud of that. And I think that really speaks to Multistack's emphasis on quality and design innovation. So the way that we see ourselves is, I think, best illustrated in our byline: originators, innovators, never the imitators. And simply that means that we invented the modular chiller. Every innovation that's made modular chillers workable in a modern building environment, we invented, and we tend not to imitate, but to simply plow our own new ground. We are, in fact, the only modular chiller manufacturer in the world that is ARI certified for shipment into Canada and the United States. We test extensively to make sure that the efficiency and capacity that we promise is what we deliver. So basically, Multistack started by providing modules of chiller capacity. Here in front of us we see a 30-ton module. Modules are available from 10 to 105 tons and potentially larger than that later this year. But we can use them to assemble a chiller of several hundred tons. And specifically the equipment that we're talking about today has scroll compressors with R410 refrigerant. And if we need to do very high temperature water, we'd be talking about R134A. But this is a typical module. This is what we would be using in our heat recovery applications and our heat pump applications. So what this is really about is using the heat that you already own. There is no heat cheaper than that which you already own. And so what we're really talking about is taking heat that traditionally gets rejected to the atmosphere, either through an air-cooled condenser or a cooling tower, and then thrown away. Bad for the environment, bad for our pocketbooks. Here, this diagram really shows a heat disposal system and a heat generation system. Heat disposal system is the chiller. Heat generation system is the boiler. And we're using electricity in the case of the chiller to move heat out of the building. But if we need heat, we're using a boiler and we're burning natural gas or some other substance, possibly fuel oil, to create heat. Not necessarily a good thing. And so how do we close that loop? How do we stop doing that? And the way that we do it is with something that is not new. It's called heat recovery. And the last time that heat recovery came upon the scene was back in the 70s at the time of the oil embargoes. And energy costs went up, and there was a lot of emphasis placed on finding alternative energy sources, not for environmental reasons, but mostly because the price of crude oil had gone sky high. But those systems, while they did exist, were difficult to balance. They had limited heat value. The controls were complicated. And what it boiled down to is when I need the heat most, I can't get it. So we're going to refine the concept. We have refined the concept into something that we call dedicated heat recovery. And that's enabled us to produce higher temperature water, to simplify the controls, to make it easier to balance, and much simpler to retrofit. So this would be a schematic that shows a typical heat recovery application. It's not specific in terms of building type. Basically, we can recover heat and use it anytime there are simultaneous heating and cooling loads. And if you think about it, most buildings have a chiller running along with a boiler firing, and specifically hospitals, resorts, certain types of office buildings, all are candidates for that. So what we have here on the top of this slide is a chiller, and the diagram represents the cooling load, and on the bottom, heating load. And a dedicated heat recovery chiller essentially straddles those two in a side stream parallel arrangement. So we take 55-degree chilled water from the cooling load. We take a little bit of that, we chill it, we pass it back to the prime mover, the main chiller, and then we take the heat from that water, combine it with heated compression from the compressors, and we pass it off. So it's actually a very simple concept. That chiller, that dedicated heat recovery chiller, hopefully that doesn't sound too oxymoronic, but that's really what we're doing. We're chilling water and we're heating water. That chiller is sized to the simultaneous heating and cooling loads. This would be another diagram showing a central plant with a boiler. The dotted line there would be the building, and you can see here that they're not communicating. The boiler and the heat load have no connection with the load. It's an expensive proposition, and it's putting about 6.5 kilograms of CO2 into the air for every therm of heat produced. And so this is another way of looking at that slide that we showed just previously. You can see that the heat recovery chiller has been integrated. We're taking heat from the chilled water loop. We're causing the central plant not to work quite as hard, and we're taking that heat and passing it off to the heat load. But specifically, I want to talk or to show 3 different scenarios of a concurrent heating and cooling load. The first scenario would be a typical chiller-boiler application, where we have a chiller and a boiler. They're not helping one another. The chiller is running at 0.6 kW per ton. That efficiency is pretty typical for a machine that you'd buy on in the market today. And we're going to assume that the price of electricity is 11 cents a kilowatt hour. And I'm going to speak to you in terms of therms. Everything is going to be in terms of therms. And that a therm is, of course, 100,000 BTU. And so just to make the mathematics more simple and easier to illustrate, everything is going to be in terms of therms. So scenario 1, the chiller would be running at 0.6 kW per ton, 11 cents per kilowatt hour blended rate. And so that a therm of cooling would cost me 55 cents. Now, that's my cooling. What about the heating, the boiler heating? Well, at $1.10 per therm of natural gas with a 95% efficient boiler, that therm of heating is going to cost me $1.45 for a total cost of $2. So a therm of concurrent heating and cooling capacity in this scenario would be $2. Now, a very typical commentary above, say, the Mason-Dixon line in North America is that, well, I don't run my chiller in the wintertime because it's cold outside and I can get all the cooling that I want for free. We actually don't believe that that's absolutely true, because economizer operation is not free. I mean, if you think about all the ramifications of bringing in outside air, it has to be filtered, it has to be heated, it has to be made up. So if you're exhausting 100,000 CFM or 10,000 CFM, or bringing in 100,000 CFM of air from the outside, you have to exhaust that same amount. So there's a cost associated with economizer cooling. But for scenario 2's purposes, let's just say that it truly is free. And let's make a comparison. So my therm of free cooling, my therm of cooling is now completely free, but my boiler is still operating at 95% efficiency and at $1.10 per therm of natural gas. So in this scenario, my cost for a therm of concurrent heating and cooling capacity becomes $1.45. So it is in fact less expensive than scenario one, but it doesn't really tell the whole story. Pardon me. So let's move on to scenario three. And as you might have guessed, scenario three is a dedicated heat recovery chiller applied as we illustrated in the diagram previously. So a heat recovery chiller operating at 1.12 kW per ton and 11 cents per kilowatt hour. So my pure cooling efficiency in this example has to be raised or has to be elevated. I'm making hot water with this chiller, so my pure cooling efficiency is actually deteriorated. But that's okay because the hot water has become free. So my therm of concurrent heating and cooling now costs $1.03. The cooling component of it was $1.03 as the result of 1.1 kW per ton at 11 cents per kilowatt hour blended rate. My heat recovery, the heating side, is giving me 125,000 BTUs of free heat. So my cost is $1.03. So if we just compare those, you can see that scenario one, conventional, scenario two, which would be economizer cooling, that's $1.45, and scenario three with dedicated heat recovery chiller, it's much cheaper. I guess what we're saying is that there's no heat any less costly than that which you already own. A heat recovery chiller is basically taking heat that you would have removed from the building anyway, and it's using it for some good purpose. So as an example, all right, Peter's going to have to bow out. Thank you, Peter, for taking the time, and we'll put it on the web. Say hello to Kenny Bright, my friend at Durham College. As an example, the type of building that Multistack has in Sparta really probably could have been done with package units, rooftop package units, but in fact we installed chilled water so that we can demonstrate heat recovery. And we have a 10-ton heat recovery chiller at the Multistack headquarters. We run it about 1,300 equivalent full load hours in the summer and about 2,000 equivalent full load hours in the wintertime. And that saves us about $5,000 a year, and that's about 5,000 therms of gas a year. So quite a bit of savings. But the cool thing is that we reduced our carbon footprint by 22 metric tons per year. So it's green in the sense that it saves us money, and it's green in the sense that we're doing something that's environmentally sustainable. So let's make sure that I'm in the right place. Pardon me, I think that my slide is missing something. And Alex, I apologize. We're missing a graph on this slide.
Mm-hmm.
Hopefully when we put it up on the web
Yes.
for you to link to, it will be there. What it is an Excel spreadsheet that shows Tri-North Middle School in the state of Indiana. And there was a comparison made where we looked at the money spent on heating with gas over a 4-year period. The first 2 years, we chilled water with electricity, we heated with gas, and spent about a million kilowatt hours per year. That resulted in a savings of 64.6% and 241 metric tons of CO2 reduced. Hopefully that's going to be up, and I'm going to move on and talk about something else. This also should show a dedicated heat recovery payback curve based on a varying natural gas cost. Where we're going with all that is that the way to maximize your investment for dedicated heat recovery is to run the dedicated heat recovery chiller as many hours as possible. And this is one of those situations where oversizing the DHRC does not actually get us anything. In order for this to work, we have to be making hot water and cold water continuously. Also, don't overventilate in winter. Remember, we said that free cooling isn't really free. And then use the hot water in as many places as possible. So, I'm going to move on, and I want to talk about heat pump technology, because what we've been talking about at this point is really not a heat pump, only in the strictest theoretical sense. We've been moving heat, certainly. Well, a heat pump usually involves a reversing valve and the ability to move heat back and forth bidirectionally at will. So a few years ago, we discovered that modular chillers also make great heat pumps, and so we can assemble some of the largest water-to-water heat pump systems in the world with a single water connection, a single electrical connection, and a single controls connection. So in the slide here, what we've got there is really a typical distributed water source heat pump system on a building, where you've got heat pumps, water-to-water heat pumps located all around the building. So you've got compressors located everywhere. You've got potential maintenance problems located all around the building. And so what we're really going to do is offer something that not only is energy efficient and provides a lower carbon footprint, but basically eliminates having multiple water-to-water heat pumps all around the building. This is called virtual movable end cap, and it's a funny name, but what it essentially means is that we can do simultaneous variable heating and cooling on a common source sink. And by closing a set of valves, hopefully you can see my arrow, but by closing the right set of valves, we can reconfigure this chiller on the fly to do simultaneous variable heating and cooling on a common source sink. And this is simply a picture of a system. But what we really want to see is the diagram here. On the front of the diagram, we'd have a hot water connection here, chilled water connections here, and on the back of the chiller, the common source sink, and in this case, a geothermal well field. And by closing the right set of valves, we can put 2 modules in heating and 4 modules in cooling. And this would be a classic 4-pipe system operating on a common source sink. And in this case, 1 module is not being used. But the beauty of it is we can take 1 module and make it do heating and have all the rest in cooling. So it's a beautiful way to do simultaneous variable heating and cooling. And this was what we call VME1, but we're moving on to something called VME2. VME1 was a system with reversing valves. Reversing valves cause pressure drop, and that takes efficiency and capacity from a refrigeration system. So we wanted to eliminate the reversing valve, and we wanted to maintain what's called counterflow. In any chiller system or heat pump system, you want to have the coldest water with the hottest gas, or the hottest gas with the coldest water. In other words, I want to create as large a gradient or log mean temperature difference as I can in order to keep efficiency up, to do best heat transfer. And so that is a weakness of a typical heat pump system. And by doing VME2, we were able to eliminate a reversing valve and maintain counterflow in our heat exchangers, and also to have a smaller electrical footprint. But let's take a look, and these are all top views of a water-to-water heat pump system. And in the diagram, or the legend at the top, it shows what each module is doing, and the secret to this application is closing the right set of valves. So this is a set of valves, this is a set of valves, valves here, and so on. And by closing the right set of valves, I can reconfigure the system on the fly and maximize my efficiency. Now, by eliminating reversing valves, I've eliminated lifting twice or using compressors twice. So I'm taking heat out of the heating load or out of the chilled water and putting it into the heating load directly without lifting it, without using the refrigeration process twice. And that is the weakness of most heat pump systems. So VME2 allows a single lift. It allows the elimination of reversing valves, and it allows taking advantage of that efficiency gain. So here we've got 3 in cooling. So on this end, that's my common source sink. On this end, my chilled water, and up here, my hot water. And in this scenario, I need 3 modules in cooling and none in heating. So I can close this set of valves and put all 3 modules to the cooling load. I can close this valve, and rather than rejecting my heat to the heating load, I reject it to the source sink. In this scenario, it's a hybrid of what we saw, 3 in cooling and 1 in heating. So I have a little bit of simultaneous load. So I close this set of valves, and I'm rejecting the heat from the 1 module to the heating load, but I still need all 3 in cooling. Close this set of valves, all my chilled water is over here, and the heat that I couldn't use on my heat load goes into the source sink. And then in this one, it's equal. I've got 3 in heating, 3 in cooling, so I've got 3 modules worth of simultaneous load. This is the most efficient example, and I've closed all the valves to the source sink, to the geothermal well field, and I'm taking all the heat from the chilled water load and putting it into the hot water load. And I've done that directly without ever having to do reversing valves or reverse the flow of water or refrigerant through any of the heat exchangers. Now, a typical commentary would be, does it have to be a geothermal well field? And the answer is it doesn't, but that's the most efficient choice. It could be a cooling tower, it could be fluid coolers or dry coolers, anything that you could use to get heat from the air or reject heat to the air or the earth could be used, but the most common and the most common choice and the most efficient choice would be to use a geothermal well field. And then this one is just another variation, 2 in cooling but 3 in heating. And as you can see, with 3 in heating, I've got this set of valves closed. All the heat that's being rejected is going to the hot water load, but I don't need quite as much chilled water, so I've got that set of valves closed. So I've got 2 modules on the chilled load, and then for this 3rd module that I'm needing heat, I'm getting it from the source sink down here. Now, if you've been thinking about this design while I've been talking, one of the things that you may have seen is that all the fluid is commingled. And if there's, not a weakness per se, but if there's one thing about this that requires extra thought, that is that in these examples, the fluid is all the same. So if you needed to provide, an antifreeze, glycol, calcium chloride, Siltherm XLT, or something like that, if you needed that to be in the well field and you didn't want to run that into the building, then you would need an intermediate heat exchanger here. But that's certainly doable. And then one more scenario, 2 in cooling, 1 in heating. So I've got 1 module rejecting to the hot water loop, 2 in cooling, and then nothing happening here. And as I mentioned before, fluid coolers can be integrated into this, especially if let's say you've got an existing geothermal well field that's been proven over time not to be quite large enough, then you can augment it with a fluid cooler. So let's see, we've got another slide that has come up blank on us. All right, this was my VME2 simultaneous load performance summary, where I showed geothermal water temperature at varying temperatures and the associated efficiencies. Probably the most important takeaway that we can't see is that eliminating reversing valves and lifting the heat right out of the chilled water into the heating load improves my efficiency by up to 43%. It's substantially more efficient. And so I realize we've moved pretty quickly, and hopefully you've been able to follow it, but what I tried to show you are a couple of ways that through the use of heat recovery modules or the same modules arranged in a heat pump system, that we can take advantage of the modular chiller system's ability to make hot water. One of the things that we didn't talk about was that these systems can make water as hot as 180 degrees Fahrenheit. Most of the time when we think about heat recovery chillers of conventional design, if you were thinking train carrier, York McQuay, a conventional type machine, they would probably want to limit you to about 130, 135 degrees. We actually have 3 different tier of temperature available, up to 140, up to 160 F or 180 F. So we can make hot water efficiently up to 180 degrees Fahrenheit. Certainly, the cooler the water that you can tolerate in your building or process, the more efficient that you can be, the less power you'll consume and the less carbon footprint that you'll have. But there are certain buildings that, for whatever reason, can't be, that the coils can't be reselected, or the coils we don't have the budget to change the coils. It is possible to make hotter water than what you would typically see from a heat pump. We've got these systems operating all over North America, and actually have installed a system very much like what we showed in the diagrams at the U.S. Embassy in Santiago, Chile, and that's working very well. So, do we have any questions? I believe that we can provide Canadian examples. I know that in British Columbia, our office out there has done this type of thing, and certainly we can provide, by parsing our database, we can provide examples of Canadian installations. We do quite a bit of business in Canada, and we will be able to provide some for the building owners in Intercan to take a look at.
Are there any other questions? Just for those who came in a little bit later, you can just write your question in the chat section at the bottom right hand of the screen.
Right. I do apologize that some of my graphs didn't come through. When we did our dry run, we had thought they were there, but the prezo that we publish on the web for you to link back to will definitely have those spreadsheets showing the numbers. And if anyone is interested, I'd be happy to share the PowerPoint with you freely.
So, okay. So thank you, Mike, again for coming out and sharing, just taking the time out of your busy day, and as well as to those who joined from Toronto. I'd just like to let you know that everything will be posted online. So I will be sending out a link shortly within a day or so. And just for those who would like to know more about Multistack, and most importantly for those who would like to access the discount through the Clinton Climate Initiative, please contact myself, Alexandra, or JT McLean, and that contact information will be sent through that email within a day. So again, if you have any questions, please email me or JT, and I hope you have a great day. Thank you again for taking the time out of your busy schedules to join us.